Okay, this is sample problem 8.1. Draw the Lewis dot symbols for the A fluoride ion, F minus, the potassium ion, K plus, and the sulfide ion, S2 minus. Okay, so if you look down at the bottom of the screen, you'll see the figure from this section. You can use that if you need to help you sort of see what we're doing, but I'm going to do it just based on my memory of the periodic table. You can refer to a regular periodic table, or you can refer to the figure down below, but I'm going to do it just based on my own memory. Now, fluoride I know is element number 9, and it's in column, or fluorine is in column 7A. That means it has 7 valence electrons. So I'm going to represent it with 7 dots. So 1, you just go around to each side. There's 4, there's 5, there's 6, there's 7. But it says to do the fluoride ion, so we want to make it negatively charged. So what we're going to do is we're going to add 1 electron. That's reduction, right? So if you add 1 electron, the claim is it goes into the valence shell. Okay? So we need 1 more electron, so I put it right there. Now, you could, in theory, write a negative here. It's probably a good idea just to write a negative next to it. Okay? Sometimes it's recommended that you draw for ions, if they're positive or negatively charged, to draw brackets around it, just to indicate that this is the Lewis dot symbol, but that whole symbol is negatively or positively charged. So I would recommend doing that as well. Your textbook asks for that, so let's do it. Let's try B. Now, B is potassium. Potassium is in group 1A, which means that it only has 1 dot, 1 lonely valence electron. So what happens when it gets oxidized to K plus? It loses an electron, right? There's your oxidation process. So you just lose the dot. So we're going to write it this way. Again, it's an ion, so we'll write it with the brackets to indicate that it's an ion, and we'll just draw a little charge here. There are no more valence electrons, right? We only have the core electrons, and so it becomes isoelectronic. The question doesn't ask for this, but this becomes isoelectronic with argon, whereas the fluoride ion became isoelectronic with neon, which is element number 10. This would be argon, element number 18. Okay, so let's try part C. Part C is the sulfide ion. That's element number 16. It's in group 6A. Okay, 6A. That means it has 6 valence electrons. Okay, it's going to become a sulfide ion, which means it's going to gain 2 electrons, right? It's S2 minus, so it's gaining 2 electrons. So that's going to give us the sulfide ion. Okay, so let's draw out the Lewis symbol for the ion. Gain 2 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. It now has 8 valence electrons. Again, it's negatively charged, so we're going to indicate that with our 2 negatives right there. Okay, and again, what that's going to give you is the same configuration as argon, which is element number 18. It's just to show you. Let's see if I can put this in here. Let's take a look at each one. Fluorine is right there. By gaining 1 electron, it becomes neon. The potassium, by losing 1 electron, becomes argon. It doesn't become argon. We're not claiming this is transmutation into a different element. We're just saying it has the same electron configuration. The nuclei are still the same as they were originally. Potassium has 19 protons and some number of neutrons, maybe 20 or so. The argon has 18 protons and some number of neutrons. Okay, and then the last one was sulfur. By gaining 2 electrons, it becomes isoelectronic with argon.